Okay, in this lecture we're going to talk about a set abstract data type. You might be familiar with sets from mathematics. A set is a collection of distinct objects. And there are a few ways that we can implement a set abstract data type. We're going to focus on one that uses bits as opposed to some other type of underlying data structure. And an application for a set in computer science would be finding the unique items in a collection of data. Since a set must have distinct elements, if you have a collection of numbers, for example, you can just add them all to the set. And because the set does not allow duplicates, at the end of processing, you would have all of your distinct elements. And so you can just review sets. I don't know how much you know. I'm going to go over it again. We're going to use the roster notation for our sets. We'll talk a little bit about membership, subsets, and then down here we'll implement some of the basic operations like union, intersection, and things like that. So first of all, conceptually we can have the empty set, and we can also have a set with a certain number of members. We can talk about the cardinality, and that's just the number of elements of a set. So if A is equal to this set, then its cardinality is going to be equal to 3. If we're going to implement an abstract data type, clearly we need to be able to add elements to the set, and we need to be able to remove elements from the set. There are particular there's mathematical notation to let you express that. We don't really need to get into the mathematics of it. One operation is called the union. And so this is just a joining of two sets. And so if you have the two sets, 1, 3, and 5, and you union it, that's the symbol for union, with 5 and 2, then you would get all of its members but removing duplicates. And so 5 is a member of both sets, but in the union there would only be one 5 because of this property that sets have, that they are distinct objects. We can also take the intersection, and this finds the common elements in two sets. So again, if I have 1, 3, and 5, and this is the sign for intersection, or the symbol for intersection, the common elements in these two sets are 5, and so the intersection would just be a set with 5 in it. Another one is complement, and this is actually the absolute complement. And in order to do this one, we have to know what the universe is. And so the universe is just a set with all the elements in it. And so let's say that the universe is equal to 1 through 10. And if I have a set A, which is just the even numbers, 2, 4, 6, 8, and 10, then A's complement, that's supposed to be a C. It does not look like a C. Then A's complement is simply all of the elements that are not in A that are in the universe. And so since I've got even numbers in A, that means that the odd numbers are going to end up in the complement. There's also a relative complement, and we'll call that the difference. And so that's going to be anything that's in one set but is not in another set. So for example, if we say B differenced with A, then this is going to be, I'm going to use a little notation here to express this, but this is going to be all of the elements that are in B, but they are not in A. All right. Another way of writing this is to say that the difference is the intersection of B with the complement. The intersection of B with A's complement. And so A's complement is how we get all of the elements that are not in A, and then the intersection gives us the things that are in B. And so for example, if I have 1, 2, 3, and I take the difference with 2, 3, and 4, all of these are present in A, and the only one that's not present in A that's in B is 1. So the difference, set difference here is 1. Then we've got the notion of a subset. Basically, you write A, the subset of B, and so every element of A is in B. And this is actually a proper subset. So first of all, A and B could be equal here, but a proper subset is every element in A is in B, and A and B are not equal to each other. And so that's just, a basic review of operations on mathematical sets. And in the next recording, we're going to examine how to implement some of these using bit manipulation.